All right, do you guys see a page in front of you that says 4.8 qualitative considerations? Okay, all right, great. All right, so here's the big idea for this section. Hold on, something's broken. Okay. Yeah, so with these variable coefficient equations, more specifically homogeneous variable coefficient equations, second order, there's really nothing that we can do about these. There is a special case though, and you guys handled that special case in 4.7. Do you guys remember doing homework with the Cauchy-Euler equations? Okay, so those were variable coefficient, right? So we were able to solve those, but those are very special cases. Most coefficients aren't going to match up with the Cauchy-Euler case. So yeah, so in general, there's no technique for solving all these to obtain an explicit closed form solution. So when we use the term closed form in mathematics, what we mean is expressible without series. We're going to talk about series later on in chapter 8, but if you can express a solution without series, that's what we mean by closed form. So those equations, you know, we're kind of have an issue with, right? The other type are the nonlinear equations. Those also meet the same fate. Really, we're going to have to wait to get to chapter 8 to talk about their solutions. Although there's something we can do in the meantime. We can handle a few of them. Okay, so what do we do if we can't really solve these things? Well, what we can do is we can at least look at the qualitative non-rigorous aspects of some of these equations. Now, we can look at the equations and maybe place a paradigm on them and kind of extract some information that way. At least we can get a feel for what the solutions are going to look like. All right, so that's the idea of this section. We're going to do most of that here. What is this? Oh yeah, okay. We're going to do most of that down here, but we're going to talk about it as we go. Okay, so like I said, these guys right here, can you guys solve these types of equations? Yeah, that's a homogeneous equation. It's second order, and the coefficients are constants, right? So we essentially have a complete theory for solving all of these. We learned this theory back in sections 4.2 and 4.3. And you remember what the solutions look like? There was 3 cases for solutions. In the first case, you had 2 distinct reals. And in the second case, you had a repeated real root. And in the third case, you had 2 complex conjugate roots. So if you remember all of the associated solutions for those, at worst case, their polynomials would be like factors of t, right? Times sinusoids. This is at e to the RT times sinusoids. Okay, so all the solutions look like that, which is nice, and we could use the existence and uniqueness theorem to show that the solutions exist everywhere. And then also, you know, since this is a linear equation, we can use the superposition principle to show that if we have 2 solutions, then we can just form any linear combination to find another solution. So we have a complete theory. It's real nice when you run across these types of equations. So what about these more troubling equations? So let's look at, for example, homogeneous in particular. It doesn't have to be homogeneous, but homogeneous variable coefficient equation. So first, let's take a look. Let's make sure we can identify the equation, right? So do you see that it's homogeneous? It's got a 0 on the right. Okay. Let's see. It's linear too, right? That's what built into the name homogeneous is the fact that it's linear. So it's linear because if you look at the dependent variable and all its derivatives, they're all separated by pluses or minuses and raised to the first power. Okay, but in this case, we have variable coefficients. So the coefficient in front of the y double prime is variable, in front of the y prime is variable, and that one's constant. But the fact that at least one of them is variables means we have a variable coefficient equation. All right, well, not much can be said about these equations, unfortunately, compared to their nicer counterparts. You know, one thing we can say, though, is we know the superposition principle holds. So if we do find two solutions, we can find another one just by taking any linear combination of those. But unfortunately, the variable coefficients really mess us up. We can't use the methods of sections 4.2 or 4.3, the auxiliary method. There's not much we can do. However, you remember in the last section, the end of the last section, we learned a method called reduction of order that could help us solve these equations. Basically, the reduction of order says that if you can find one solution to this equation, just one, if you're able to figure that out somehow, then reduction of order will allow us to find another one that's linearly independent. So then you have two linearly independent, and that's good enough to construct the general solution. But you still have to scrap together a solution. And unfortunately, that can be really hard, right? So there's no method for finding two or one, let alone two. So there's really not much we can do. However, you might get lucky. And in the last example of section 4.7, we got kind of lucky because it was easy to spot a solution. But in general, not so. This equation right here is an example of an equation called a Legendre equation. And these equations arrive in the analysis of wave and diffusion phenomena in spherical coordinates. Okay. As we progress through this section, you're going to notice we're going to run across a lot of equations, and I'm going to give you names of equations. I don't need you to memorize them or anything. Just take note of them because you're going to run across these, many of these later in your differential equations class or in your physics classes. So for example, we're going to go through a bunch down here. The area equation, Bessel's equation, modified Bessel, Duffing, van der Pol, and motion. And if you click there, there's a list of a bunch of well-known differential equations that you might run across in your studies. Okay, so that's an example of a Legendre equation. Okay, so that's pretty much all we know about the variable coefficient equations. What about nonlinear? So first, let's identify these. That's nonlinear, right? So why is that not, why is that, it almost looks linear. What's making it nonlinear? You guys can unmute yourself or in the chat's fine too. Oh, got some answers. Yeah, the y squared, right? You got to have y to the y and all of its derivatives have to be to the first power. So the second derivative is to the first power. This one's to the second power. So there's the issue right there. This one is a nonlinear equation. And then the issue here would be the y to the 1/3 power. So both of these are examples of nonlinear equations. There's a ton of others that you can come up with too. Okay, so unfortunately for these equations, we know even less. They're not linear, so we can't use the superposition principle. It doesn't hold. Also, we don't have really any method for finding solutions. There's something that we're going to learn in this section called the energy integral lemma, which is kind of like the reduction of order theorem that we learned in the last section. It'll help us a little bit find solutions. Okay, but that's pretty much it. And this energy integral lemma only applies in very specific situations. So, you know, it's not going to work most of the time, but we'll talk about that. Okay, so what does this mean? This means that for these functions, these ones that we're working with in this section, most of our efforts in solving these are going to result in dead ends. So what are you going to do if every time you solve, it's not, you can't do anything? Well, why don't we at least look at, you know, maybe how the solutions behave? Maybe there's a way we can look past this, place a paradigm on it, like the mass spring oscillator, and then maybe we can gain some insight into what the solutions might look like. That's what we're going to do. We're going to use the mass spring oscillator to do that. But first, let's talk about the energy integral method or energy integral method. Or I'm sorry, it's the energy integral lemma. And it's for nonlinear equations. Okay, here we go. So it only works, like I said, in a very special circumstance when your nonlinear equation has a very particular form. So here's the form right here. So if you happen to have a nonlinear equation that has that form, you'll notice that there's no first derivative term. You got a second derivative, and then everything is in terms of the 0th derivative, and it can be any function of y. So if you have it written like this, and the function f that you constructed is a continuous function, and it doesn't explicitly depend on y prime, and doesn't depend on the independent variable t, then what you can do is you could let capital F be the antiderivative or unantiderivative of that function f. So you're going to have to do a little calculation there. And then once you do that calculation, the energy integral lemma says that this equation must be true. Now, what we have here is we started with a second degree equation. And what we have now is a first degree equation. See that? Okay, so we've essentially reduced the order of the equation. Okay, and you'll notice that I've got one constant appearing there. So yeah, so that's the idea. Now we're going to use this thing to help us solve some of these equations, but it's not quite done yet. That's the energy integral method, but we're going to take a couple steps further than this. So what we're going to do is go ahead and solve for y. We're going to try and solve for y. So we're going to take this equation. So let me write it down again. Okay. And we're going to try and solve for y. So the first thing we do is we probably move the f of y to the right, like so. Something's wrong with my mouse. Hold on a second. Try this again. There it goes. Okay. All right. So we're good there. Then what we like to do is multiply both sides of the equation by 2. And that will give us this equation. Then we're going to take the square root of both sides. And when you take the square root of both sides, this is going to introduce a plus or minus. Right? So we've got y prime equals plus or minus the square root of 2 times that big F function of our solution y plus our constant k. Okay? So what we have here, if you think about the left-hand side, we can actually express this using Leibniz notation. Do you guys notice that's a separable first-order differential equation? It's been a while since we did those. Those were chapter 2, I think. Okay, so it's definitely separable. You'll notice to be separable, basically, you want to be able to move all the y's on one side and all the t, the independent variable, on the other. So we can easily do that. What we'll do is we'll move the t to the right, and we'll move pretty much this whole thing to the left. So now we've got everything separated, all the y's on the right and the t's on the left. Is that okay? Okay. And then we're going to integrate. Okay, so we're just going to integrate both sides. Okay, so the integral of t is t plus some constant, right? And then you could, this integral, of course, it's going to depend on what the function f is. So I'm going to leave it in general terms like so. So there we have it. Assuming you can integrate this function in here, what we have is an implicit solution, assuming you can do that integration. And you should notice that there's going to be 2 parameters involved. And that makes sense because this is a second order equation. All right, so this is the form we're actually going to use because this is the implicit solution. It's implicit because we don't have y solved for. You're going to have to do the work, right? And actually evaluate the integral, and maybe or maybe not, you can move y to solve for it, but it really is, as it's expressed, an implicit solution. Okay, so it turns out that we can kind of use this to reveal some kind of surprising facts about nonlinear equations that are going to feel a little foreign to you. So let's take a look at this first one. So first example. So first of all, make sure you identify that as a nonlinear equation. What makes this nonlinear?
Y squared.
Yeah, the y squared, that's the problem. Okay, so it's nonlinear. All right, okay, so it kind of looks like it might apply for the energy integral lemma. So let's look at the lemma. Okay, so as long as we have this form, y double prime on the left, which we have, and then f of y, so the function has to be continuous. It can't contain y prime and can't contain t. Okay, so we have 6y squared, that's a continuous function. It doesn't contain y prime, doesn't contain t, so I think we're good.
Can it have
All right, make sure you,
constants on it?
what's that?
Can it have constants?
Yeah, that would be fine.
Okay,
Yep.
thank you.
So it can be any function that's continuous. So if you take a constant on the end, it doesn't do anything to the function other than raise it up and down. So it's not going to change its continuity. It just can't contain these guys. That's the issue. Okay, so we're good to go there. So the next step is you're going to basically find one antiderivative of little f, and you get to pick what it is. So what we do is just evaluate the integral and then just pick one, pick a convenient c value. All we need is one value for f. So let's go ahead and integrate. Okay, so we're going to integrate f of y. Now f of y is 6y squared, so we're going to plug that in. Integrating 6y squared, we get 2y cubed plus c. And since we can choose any of these functions, what you want to do is choose the value of c that's most convenient for you. So in this case, I think choosing a value of c equals 0 is most convenient. So that's going to be our function capital F. All right, next. All right, the conclusion of our theorem says that this equation must be satisfied. Essentially, we've reduced from a second order differential equation to a first order differential equation. All right, but we're actually going to take it all the way down to here to this implicit solution. So let's see what we do. Yeah, we're going to go straight to the implicit solution. So I'm going to refer to equation. Go ahead.
We typically always have c equal to 0. Is that just like general rule because it's easiest?
Yeah, it depends. It just depends on the problem, the function. Sometimes choosing another constant is easier than, or maybe you're not allowed to choose c for some c equals 0 for some reason. So, choose whatever. It should be relatively obvious what the easy one is. But yeah, I mean, when it's a plus c, definitely a 0 would be the easiest. Okay, what else here? Okay, so what we're going to do is use our conclusion down here. This was our extension basically that we proved. We proved that this was an implicit solution. So let's go ahead and plug it in. So we've got t equals, and then I'm just going to plug in my function f right there. So here's my function f, 2y cubed, ignore the c. So we'll plug it in there. And then we're going to add a constant k. And then we're going to add this other constant c. Okay, so what this is that's basically an implicit two-parameter solution to the differential equation. Okay, so we're being asked to basically use the energy integral method, which we did, and then explore the solution. So let's start exploring some of these solutions. Okay, so there's two parameters there, right? So instead of trying to look at both parameters at the same time and trying to mess around with that, let's simplify this a little bit. We're just going to look at some solutions. So why don't we choose solutions where k equals 0? Okay, so we'll choose that to be 0. So that's basically going to reduce this a little bit to this. And let's also choose solutions where we're looking at the positive values. This is just an investigation, right? I'm not looking at all of them. So I'm just kind of picking some of them to look at. And then finally, we've kind of got it down to something that we can integrate. So integrating this guy, rewriting and integrating and absorbing the constant, we'll have something that looks like this, right? So you have t equals negative y to the negative 1/2 plus c. Now, what we want to do is write this explicitly. So what we do is take our solution here and we would solve for y. So you would subtract c to the other side, negate. Do you guys see how they got to here? You guys do the algebra? Why don't you do the algebra yourself? But you should be able to get to here from here algebraically. Okay. All right. So once you solve for y, we basically got a one parameter solution. I already chose k to be 0, so one parameter is gone. So this is our one parameter solution there, c. Okay, but the thing is, this is kind of weird if you think about it. We've set one of the parameters to be 0, and now we have this other free parameter c. So if you were to graph this function, what you'd find is you have something called a singularity at t equals c. The function basically blows up there. You guys might remember if you put this function into Desmos, you'd see it kind of blow up there. Basically, that's what a singularity is. It's where a function kind of blows up. It has some, specific meaning. It has to do with something called analyticity, which is infinite differentiability, which we'll talk about later on. But basically, yeah, we've got this kind of weird behavior at t equals c. And the problem is that, that value of c can shift depending on the initial conditions. Now, this never happened before. When we had linear equations, we never had to worry about this kind of situation. We just had an interval and it was always the same no matter what the initial conditions were. So this is definitely different. It's strange. What else? Also, this is kind of strange. If you pick different constants for c, like say I had initial conditions which led to a c value of 1. And then I had, let's do another problem where I had initial conditions that led to a c value of 2 or 3 or whatever. All of these functions are actually linearly independent, which is kind of strange because in the constant coefficient case, when one of the constant was 0 and we changed the c value on the second constant, then all of the rest were linearly dependent. Yet in this example, it seems like whenever we change the c value, we're getting all of these extra linearly independent solutions. Okay, so that's kind of strange. But this is probably the most important thing that's a little different. Even though we have an infinite set of solutions, we can't really assemble one that satisfies at least some of the initial conditions. Unlike constant coefficient equations, which always have a solution, a unique solution. So I'll give you an example. Let's say that we were dealing with this same differential equation, but here's the initial conditions. Okay. So now we have an IVP, and you guys remember how to solve IVPs, right? You take your solution, differentiate it, second derivative, or I'm sorry, we need the 0th and the first derivative in order to use the initial conditions. You plug a 0 in here and set it equal to 1. You plug a 0 in here and set it equal to 3. And what'll happen is you'll get this set of equations. This is nothing new. But the problem is there's no c values that satisfy this set of equations. Okay, so what does this mean? It means that the differential equation doesn't have a solution for these initial conditions. All right, so what's just happened? Basically, what this says is that these nonlinear equations, we don't get existence of solutions. We can't guarantee the existence of solutions. Remember, for linear equations, we could. We had the existence and uniqueness theorem. But for nonlinear ones, we don't have existence. Okay, so that's the first kind of example we've worked through. By the way, I labeled this one non-existence. You're going to see in this next example, I'm going to give you a differential equation and show you that this one does have a solution satisfying a set of initial conditions, but it has more than one, so you don't have uniqueness. So let's work through that one now. All right, so this time, there's our nonlinear equation. Let's check to make sure it has the right form. I'll go through this one a little faster, okay? So first of all, it's nonlinear because it's y to the 1/3 power. You want to make sure it has the right form. So is that okay? Is the form okay? If you look at the right side, it just has to be a function of y. It can't have y prime or t in it. So we're good to go there. Okay, so we take our function and we integrate it. So that's a fairly easy integral. You'll get 18 to the 4/3 plus some constant. Just choose c equal to 0. All we need is a single function, capital F. So there's our function in red that we're going to use. All right, then we're going to plug that into our 2-parameter implicit solution that we derived above. So you just plug it right in there for F. Yeah, and there's basically our 2-parameter implicit solutions. You can see the parameters there. We've got a C parameter and we've got a K parameter. Okay, and assuming you can do the integration, that K would turn into some other constant, but it'd still be, you'd still have 2 constants there. All right, so, we want to explore the solutions, but there's just so many of them and it's getting complicated. We don't need to look at all of them. Let's just look at some of them just to get an idea. So why don't we simplify this? Why don't we choose the positive, the ones where we have a positive integral, and then we'll choose values where the constant K equals 0. And that's going to simplify this to those guys. So now we're looking at a 1-parameter family of solutions. And we can integrate this. We have to do a little work here. I'll let you guys do that on your own. And we'll get down to something that looks like this. Now that's an implicit solution. Let's solve for y. And if we solve this for y, you guys can do the math there. You'll end up getting this solution, 2t minus c cubed. Okay. Again, you guys should probably work through the algebra and make sure you can get step to step. But for now, we don't want to spend our time working through that. All right, let's suppose that these are the initial conditions. Okay. All right, well, what does that mean? Well, if we use the initial conditions, we need the 0th derivative, which we have, and then the first derivative, and then you plug in a 0 here and set it equal to 0, and plug in a 0 into the derivative, set it equal to 0. What you'll notice is that what has to happen is c equals 0. So you do get a solution. You get existence. So we've got existence. So what that means is this is definitely a solution, 8t cubed to that IVP. But here's the problem. This is also a solution to the same IVP. All right, you'll notice that this function satisfies that equation, and its derivative satisfies that equation. And if we took this function and we plugged it into the original problem, it satisfies that equation. So that's definitely a solution. It's a trivial solution, right? So we've got 2 solutions that satisfy this IVP. So you got a curve here and a curve here, and they're passing right at that point. So that means we don't have uniqueness of solutions to nonlinear equations, unfortunately. Right? Linear equations are great because we've got existence and uniqueness, and we have the superposition principle, and everything kind of lines up nicely. But when you move off to nonlinear, it just gets really ugly really quick. So hopefully it shouldn't be too surprising that when we're trying to solve these things, it's a lot harder. In fact, most of them we can't solve, even with series methods that we're going to discuss later. So most of the time we'll have to use some kind of numerical techniques. All right, so that's the energy integral lemma. All right. Do you guys mind if we pause just for a minute? I want to get something to drink. You guys take a break too. We'll take like about 5 minutes. Is that okay? Okay, I'll be right back. All right, guys, we're back. Check a setting here. Okay. All right. So, okay. So for the rest of the section, we're going to investigate some qualitative features of both of these types of equations, the variable coefficient equations and the nonlinear equations. All right. So let's take a look. We're going to do a whole bunch of them. So clearly, nonlinear equations, they act kind of weird. We don't even have existence and we don't have uniqueness. So it's not surprising that, and we don't have linearity, so you don't have the superposition principle. So there's really not much you can do with these things. So what do you do? Well, what we can do is we can take our mass spring paradigm and we can kind of place them on some of these problems. And we can use our interpretation of what the coefficients mean. Oops. So like, yeah, for what the coefficients are and this guy on the right, to maybe interpret what the solutions would look like. So let's quickly review this. So remember, this is our mass spring paradigm for the motion of a mass spring oscillator, where m is the mass of the object that's being bounced around, right? And then what does B represent? Oh, it's right there. B is the damping coefficient. That's basically the amount of friction, right? So one way to think of the friction would be like, imagine a spring underwater that's kind of slowing its motion down. The way I displayed it in my animations is I made a piston, and then the piston was slowing it down by a little kind of a stopper that I was widening, and it would slow the thing down over time. In fact, I might have it here. Oh, it's not in this one, but that's okay. All right, and then the K value, well, the K value is just the spring constant. So every spring has some constant number associated by it using Hooke's law. It basically tells you the stiffness of the spring. Okay, and then over on the right of these equations, we have our external forcing function. So this would be a driver that's basically shaking the supports of the wall that's holding the spring, right? So in this particular section, we're dealing with all, oh no, this is 4.8. Yeah, okay, so we're going to keep this general. So yeah, another way to think of this is that this is the sum of all the external forcing functions outside of the internal system. Everything in here, this is internal, right? The mass, the friction, the spring constant, the forces from those is internal. So let's take a look. First one is Airy's equation. So let's apply the mass spring paradigm to this particular equation. So what you want to do is try and think of it in this form and identify the mass, damping coefficient, spring constant, and external forcing function. Okay, so let's take a look. So first of all, you want to note that the coefficient in front of the y double prime is a 1. So that means your mass is constant. That's the same as, you know, that's nice that it's constant. We don't need to do much for that one. And then you'll notice that there's no damping. So there's nothing slowing us down. So B equals 0. And you'll notice that the spring constant is T. Okay, the spring constant is stiffness. So remember, with these problems involving time, we like to start time at T equals 0. Hey. Okay. We like to start time at T equals 0 and let it go off in the positive direction. So what's going to happen is if T goes off to infinity, what's going to happen is the stiffness is going to increase steadily over time. Does that make sense? Okay. Yeah, so as T increases, the stiffness should increase. So that's something that we could use. And then also you'll notice the right side of the equation is 0. So that means there's no driving force on this oscillator. Okay, now we talked about this in a previous section, but when we're solving oscillators that don't involve friction, we can use this symbol omega, which is basically the angular frequency of the oscillator. So in this case, the angular frequency is given by square root of k over m. This formula is going to come up over and over again. I'll derive it again in the next section, but I'm just writing it down again. So this is our angular velocity, square root of k over m. Okay, so the k value is t, and the m value is a constant. So what's going to happen is you're going to have a t over an m. And as we let time go off to infinity, what's going to happen is your omega, your angular frequency, is going to increase to infinity. Now, as far as what angular frequency is, that would be the speed at which the thing oscillates. So what this is saying is that as time elapses, over time, this thing should oscillate more and more. Does that make sense? That's the angular frequency. So that's how much it's oscillating. We'll talk about this in more detail in the next section. Okay, so we can expect the angular frequency to increase over time. So we've kind of got two things going on, right? We have the stiffness increasing over time, and we have the angular frequency increasing over time. Okay, since the stiffness is increasing over time, what's going to happen with this oscillator is the spring is going to get harder and harder to stretch over time. All right, let's kind of use what we've discussed through this paradigm to maybe come up with a graph of what a solution might look like. Now, there's lots of solutions based upon the initial conditions, but let's just graph one of them based upon what we know. Take a look at this guy here. So first of all, do you guys notice that the stiffness, this seems reasonable considering this is the motion of the mass of the object. And you'll notice that it's springing up and down less and less over time. So does that seem reasonable as far as the spring stiffness? It's getting more stiff, so it's not going to go up and down as much. And then the angular frequency is increasing over time. So that means the number of times that it bounces is increasing. And so what you'll notice is as you move to the right, the speed at which it's oscillating is speeding up. So it's kind of going slow and then faster and faster. Right. So you notice the periods over on the left are longer than the periods on the right. It's another way of saying it. Okay. All right. So that's what we're going to be doing. Most of your homework and stuff in this section, most of what we're going to be studying is trying to figure out basically what qualitative conclusions can we make about solutions to these equations rather than finding the solutions, just what can we say qualitatively about them? Okay, do you guys have any questions on this one? All right, good. Sebastian's good. Anyone else? Okay, all right, we'll keep going. All right, so that's called the area equation. Here's another one called Bessel's equation. So again, we're going to apply the mass spring paradigm. So you can kind of see this one's lined up. Can you see that the mass is 1? The coefficient of friction is 1 over T. The spring stiffness is 1 minus n squared over T squared. And the external forcing function is 0. Do you guys see that okay? Okay, I'm just writing down the coefficients, right? All right, so the first one's easy. That one's constant. And then the external forcing function, that one's easy. It's just 0. So, but you can see that the coefficient in front of the y prime and the coefficient in front of the y, those are variables. So I kind of highlighted them in red, and we're going to analyze each of them and see if we can figure out qualitatively, how does this affect solutions? Okay, so let's look at the first one. So we have the friction is 1 over T. Now remember, we're looking at solutions as they're mapped out over time. Okay, so over time, 1 over T approaches 0, right? So what that means is, first of all, your damping's definitely positive. So we're in the real world, right? It's always a positive number because T is positive. But then also notice that the damping is decreasing to 0. So that means that over time with this mass spring oscillator, what's going to happen is you're going to have less and less friction. All right, so when you're doing these problems, you probably want to write down these ideas next to them because there's going to be a few that'll kind of jump out at you. All right, and then what about the spring constant? Oh, this is how springy we are, right? So 1 minus n squared over T squared. All right, let's go back to the equation just for a minute. This is called a Bessel's equation, and it's true for T greater than 0 where n is some positive integer. So essentially what happens is you have to pick a positive integer. So let me pick one. All right, that's one of Bessel's equations. All right, and it's a fixed constant. So then the question is, what happens to this guy over time as T increases? All right, well, you might notice that as T increases, this term on the right, that term on the right is going to go to 0. because the denominator is going to go to infinity t squared. Okay. Also, you'll notice that when t is greater than 5, the stiffness is going to be positive because you'll be subtracting a number less than 1. Before that, it'll be negative. So what we can say is it appears that the stiffness is positive once you go out far enough in time. And also it increases to 1 over time. Okay, so it doesn't increase forever. It just, with no upper bound, it increases up to a constant number 1. All right, so let's take a look at the angular frequency. Same formula for the angular frequency, omega, so square root of k over m. In this case, k is variable. Let me replace that with an n again. All right, so n is just a fixed constant. So replace k with that, with its variable function, and then it simplifies. And notice as we take the limit as t goes to infinity, what's going to happen is this guy is going to go to 0. Right? For any fixed value of n that you're given, eventually t is going to pass it. It's going to way surpass it. The denominator is going to kill it, and the fraction will go to 0. So then you just have square root of 1. Okay. So, yep. So the angular frequency increases to 1. That's what we concluded here. By the way, this is probably a good point in time to review a little bit of your trigonometry. The relationship between, we call this the angular frequency, omega. The units of measurement are radians per second. Then there's the natural frequency, which is omega over 2 pi. The units of measurement are cycles per second. And then there's the period, which is just a length. Okay. All of these are basically telling us how fast the motion is oscillating. And we'll do more of this in the next section. But just keep in mind that if you happen to have the angular frequency, you get the rest for free. You get the natural frequency for free because you just take your angular frequency and you divide by 2 pi. Or if you take 2 pi divided by the angular frequency, you get the period. So this is the main one. If we could find this one, then we get the other 2 for free. Okay, what else do we know? Well, we know that the damping is positive and it decreases to 0 over time. So below is a graph of maybe a couple of possible solutions. And actually, if you were to solve the equation, these are the solutions. A couple of them. Let me turn this to output. All right, so let's take a look. All right, so this function in blue, we label it with a j sub 1/2 of t. And that other function in y, that's another solution. So I'm showing you 2 possible solutions for different initial conditions. Okay, so, but you do want to notice a few things, right? Let's make sure that this satisfies our criteria, our qualitative criteria. Let's see, damping is positive and decreasing over time. So it seems, okay, well, it's acting in the right direction. Damping is definitely positive because it's slowing it down, but it's not slowing it down as much as we go to the right, which is fine. There's nothing pumping energy into the system. So, and then stiffness is positive and increasing over time. Yeah, kind of hard to see with this one. But I wanted to talk more about these 2 guys right here. These are called Bessel functions. If you take this function and you plug it into Desmos, what you'll get is that blue function right there. And if you take this function and plug it into Desmos, you'll get the black function. So it turns out that solutions to this differential equation, this Bessel's equations, are actually really complicated. And for nearly all of them, you're going to have to use power series. except for some of them. Some of them you don't have to express with power series, and this would be an example of one, and that would be an example of another. We call these types right here, we call them Bessel functions of order n. In this case, order n equals 1/2. And this would be the first kind, and that would be the second kind. So you're going to run across these possibly in a future physics class. Okay, so your order n is this guy right there. All right, so when the order n is a half integer, for example, like 3/2 or 5/2 or 7/2, anything in the middle, what'll happen is you'll get this nice closed form solution, kind of like these guys. But for all the other values of n, what'll happen is you'll have to use numerical approximation. Okay. If you're interested in the study of these type of functions come up when you study electromagnetic waves, the Schrodinger equation, or surface waves generated by microtremors. These equations right there. All right. All right, this is a slightly modified. Do you see the difference between these two? The Bessel's equation and the modified. What's the difference?
The minus sign.
Yeah, it's just the minus sign. So it changes basically the springiness is going to change a little bit. So yeah, the constant's still 1, but the mass is still 1, the forcing function is still 0. The friction still is positive and decreasing to 0 over time, and the spring stiffness, that negative right there changes things a little bit. What happens is now if you let t go to infinity, this guy's going to go to 0. So what'll happen is it'll approach -1. It'll decrease and approach -1 over time. Unfortunately, -1 is one of those non-real world phenomena, right? If you have a spring constant of -1, do you remember what happens when you have negative spring constants?
Doesn't that mean it's just like adding energy into the system?
Yeah, it's basically you have a world where springs act completely the opposite of what they do in our world. So instead of when you stretch them, instead of bringing you back to the origin or pulling you back towards the origin, it's basically going to expel you. So the further you go away, the more it's going to expel. So what's going to happen is as soon as we move away from the origin, it's going to want to just keep expelling us forever. So this is not great for our real world way of looking at it, but it makes sense. It's just the opposite of what happens in our real world. Okay. So yeah, so we can expect that the motions will exile to plus infinity or negative infinity, and they'll do it real quickly because once you move away from the equilibrium, this guy k equals -1 is just going to throw the thing off to infinity. So that blue one right there is an example of a solution. Now, it is possible to have one that doesn't expel to infinity. However, it's a very limiting situation. You have to have it such that your initial conditions, whatever your initial position or initial velocity are, they have to be such that you push the spring or push the mass downward or upward, but towards equilibrium at the exact amount so that it balances just perfectly at equilibrium. It's not really going to happen. I mean, it's so unstable. So in real life, this wouldn't happen, but theoretically, it is possible for you to find a solution that does this. But all the rest of them, all the rest of them are just going to do this. They're just going to expel to plus or minus infinity. Okay. Yeah. So we call these ones, these solutions IN, and then the KN, this unstable equilibrium solution. Those are called modified Bessel equations. Of order 2 of the first and second kind. Yeah, these aren't very well behaved, and they're not expressible with series either. Oh no, we can't express them with series. Actually, I don't know. We'll see. We'll find out. Okay. In any case, they're used in statistical analysis with spherical distributions and probability. All right, here's another one, the Duffing equation. So we're going to place the mass spring paradigm on it. All right, so here it is. apply the mass spring paradigm. Why does it look all funny? Oh, I factored it. Let me write it below. Let's leave it like this. Yeah, let's leave it like that. All right. Okay, so if you write it like this, what you'll notice is that the coefficient in front of the y term involves a y term, which is kind of strange. You don't have to. You can expand it out and you can express it however you want, but we get to choose. So we chose to express it this way. You notice the mass is 1. There's no damping. And the spring constant is 1 plus y squared. All right, so let's investigate this. And by the way, the forcing function is 0. So you want to imagine a mass spring system with all of those conditions, except the spring constant is such that it's 1 plus y squared. Y is basically the displacement from 0, displacement from equilibrium. And since we're squaring it, we're going to get a positive number, no matter if y is positive or negative. So at minimum, k is going to be 1, and it's only going to get larger, right? So the spring stiffness is positive, and it's at least 1 and increases as the displacement increases. Are you guys following this? This is kind of like calculus 1 stuff where we have you kind of, identify what is a function doing as we let t approach a. It's kind of the same stuff. It's just a little more advanced, okay? Okay, so what's happening here? So there's no friction. There's no damping. And the spring constant is positive. So that's a good thing that the spring constant is positive. At least that's happening in our world where spring constants are positive. However, for this particular spring, it looks like the spring constant is going to increase dependent on your distance from the origin. Okay, so what's going to happen is, and there's no friction. So when this thing is going to repeat infinitely. So what's going to happen is your angular frequency, which is k over m, is going to be 1 plus y squared over m. So what's going to happen? This is going to increase the numerator. So the angular frequency is going to increase. Is it volting in a shorter period? Yeah, okay. Yeah, so it's going to speed up a little bit. So the one in black is the one that's sped up as we increase k. So this one over here would be for a smaller k, and then this one would be for a larger k. All right, so the angular frequency is increasing. But also what happens is as you move further and further away, that k value is going to increase. So as you move further up or further down, your displacement is larger, which means when you square it, it's going to get even larger. So what'll happen is you'll kind of have this pinching effect. It won't quite, like the black one isn't quite sinusoidal. It'll be kind of a pinched sinusoidal. It'll really be adding more and more pressure to it the further we get up towards the further we get up with larger values of y.
What you're saying is the amplitude won't get bigger, but the wavelength will get shorter, essentially.
Say that
Like
again?
the amplitude won't get bigger, but the wavelength will just get shorter? Is
Right.
that, okay.
Yeah, the wavelength or angular frequency or period, the angular frequency will increase, the period will decrease. Yes, exactly. Yeah. Okay. Any other questions on that? So finding the solutions to these guys is rather complicated, but in any case, we could graph a couple of the solutions down here. This is for smaller k, and this is for larger. Okay, so where this kind of equation comes up, the Duffing equation, it comes up in the design of matrices for therapeutic reasons. So increasing stiffness affects the built-in popular matrices, such as spring, grows stiffer as the mass moves further away, but it restores its original value when the mass returns. Oh, that's interesting. It's also used in the study of chaos too. Okay. All right. Couple more. I thought there was a video in here somewhere. Did I skip it? Huh. Oh, well. All right. And then there's the van der Pol equation. So this equation is used in the study of electrical oscillations in vacuum tubes, and it's been used a lot in the physical and biological science. Actually, on the cover of our textbook, it actually has a lot to do with the world's most accurate pendulum clock. All right, so this is the van der Pol equation. All right, so let's rather than try and solve it, right? That's not what we're doing this section. Let's just see if we can gather some qualitative aspects of it. So the first thing is, if we use the mass spring paradigm, the mass would be 1. Coefficient of friction would be B times -1 minus y squared. We'll take a look at that below. The spring constant is just 1. That's like normal. And then the external forcing function is 0. So everything's like normal except for this one, the friction. So you got to imagine a situation where you have a mass spring oscillator and the friction obeys this equation here. So let's look into this more deeply. All right, so basically, let's ask ourselves, when is the friction positive? When is B greater than 0? Okay, for B to be greater than 0, this would have to be greater than 0. So we'll set it greater than 0. Okay, so let's solve this inequality. If we distribute this negative, we'd have this inequality. If we add the 1 to both sides, we have that inequality. If we solve this inequality, y squared greater than 1, essentially we're looking at the magnitude of y is greater than 1. So you got to imagine this. You've got a mass spring system that's bouncing around. Once the mass spring system gets further away than 1 unit from equilibrium, so further away this direction or further away this direction, 1 unit from the equilibrium, what'll happen is the spring constant, I'm sorry, the damping will kick in. It will go positive once that happens. So as it gets further away, the damping will turn on like real world damping and it will slow it down. However, in the opposite case, if the magnitude of y is less than 0, what'll happen is the B value will be negative, in which case you'll have energy pumped into the system. Okay, so that's a very strange situation. If the mass spring oscillator is within 1 unit from equilibrium, it's going to the forcing part of the forcing term is going to pump energy in the system. But if it gets too far out, it's going to drain energy from the system. So here's what's going to happen. You're going to basically get this limit cycle. So let's say our initial conditions put us up here. Here's 2 possible solutions. But it's going to force us into this limit cycle where once we, it's going to kind of act like a normal mass spring system when we're up here, maybe above 1. But then once we get in here, when we're within 1 from the origin, it's going to pump energy into the system and it's going to push it out. But once it gets out above, beyond 1 unit, it's going to slow it down again. It's only going to get worse as it gets further away, and then bring it back again. So it's like this continual kind of pumping energy into the system, draining energy into the system. So it's like a combination of 2 worlds, 2 physics engines acting on this object. Okay, I'll let you guys spend some more time, looking into these and trying to analyze them. But, that's kind of the idea of the section, is to take the time to do that. Okay, and lastly, we're going to take just a basic look at the motion of an undamped pendulum. Oh, this is where I have the video, I think. Yeah. So let me show you this video first. I'm not sure if it's going to work, but let me press play. Can you guys hear that audio? Let me try this again. All right, let me turn up the volume. Hold on.
A simple example, a pendulum. How does this angle theta that it makes with the vertical change as a function of time? This is often given as an example in introductory physics classes of harmonic motion, meaning it oscillates like a sine wave. More specifically, one with a period of 2 pi times the square root of L over G, where L is the length of the pendulum and G is the strength of gravity. However, these formulas are actually lies, or rather approximations which only work in the realm of small angles. If you were to go and measure an actual pendulum, what you'd find is that as you pull it out farther, the period is longer than what the high school physics formulas would suggest. And when you pull it out really far, this value of theta plotted versus time doesn't even look like a sine wave anymore. To understand what's really going on, first things first, let's set up the differential equation. We'll measure the position of the pendulum's weight as a distance x along this arc. And if the angle theta that we care about is measured in radians, we can write x as L times theta, where L is the length of the pendulum. As usual, gravity pulls down with an acceleration of g, but because the pendulum constrains the motion of this mass, we have to look at the component of this acceleration in the direction of motion. A little geometry exercise for you is to show that this little angle here is the same as theta. So the component of gravity in the direction of motion opposite this angle will be negative g times sine of theta. Here we're considering theta to be positive when the pendulum is swung to the right and negative when it's swung to the left. And this minus sign in the acceleration indicates that it's always pointed in the opposite direction from displacement. So what we have is that the second derivative of x, the acceleration, is negative g times sine of theta. As always, it's nice to do a quick gut check that our formula makes physical sense. When theta is 0, sine of 0 is 0, so there's no acceleration in the direction of movement. When theta is 90 degrees, sine of theta is 1, so the acceleration is the same as it would be for a free fall. All right, that checks out. And because x is L times theta, that means the second derivative of theta is negative g over L times sine of theta. To be a little more realistic, let's add in a term to account for the air resistance, which maybe we model as being proportional to the velocity. We'll write this as negative mu times theta dot, where mu is some constant that encapsulates all of the air resistance and friction and such that determines how quickly the pendulum loses energy. Now this, my friends, is a particularly juicy differential equation. It's not easy to solve, but it's not so hard that we can't reasonably get some meaningful understanding out of it. At first glance, you might think that the sine function you see here relates to the sine wave pattern for the pendulum. Ironically, though, what you'll eventually find is that the opposite is true. The presence of the sine in this equation is precisely why real pendulums don't oscillate with a sine wave pattern. If that sounds odd, consider the fact that here, the sine function is taking theta as an input, but in the approximate solution, you might see in a physics class, theta itself is oscillating as the output of a sine function. Clearly, something fishy is afoot. One thing that I like about this example is that even though it's comparatively simple, it exposes an important truth about differential equations that you need to grapple with. They're really freaking hard to solve. In this case, if we remove that dampening term, we can just...
All right, let me back off here. All right, the only reason I show you that is because this is kind of surprising for those of you that have taken physics before. In your physics courses, oftentimes what we'll do when we're doing one of these these pendulum problems is we'll use a sinusoidal function to approximate theta. But the thing is it's not really a sinusoidal function. For small values of theta, it acts sinusoidally. But the further you get away, the further that you move the pendulum up, the more you have this kind of this behavior right here. It starts looking more and more like this, like so. So, you know, here they are kind of next to each other. They're sinusoidal in blue. And then the black one would be the one of the actual motion. Okay, so we're going to work through one of these, but I just want to show you that video. So make sure you know that these aren't exactly sinusoidal solutions. And you'll see that Okay, so if you want to work through this, I didn't go through all the specifics here, but basically we're using a version of Newton's second law of motion. L is the lever arm, basically, which is the distance from here to here. Theta is positive when we're swinging over to the right, and it's negative when we're swinging to the left. And then, of course, M is the mass. And G is the gravitational acceleration, and it's pretty much all we need. So if you have all those and you employ Newton's second law of motion, you can come up with this second order differential equation, which basically describes theta. Right? If you solve this for theta, it will tell you the angle over at any time. Okay, and you can rearrange the thing so it looks like this. It's written a little nicer this way. So now what we're going to do is we're going to apply the mass spring paradigm. So we're going to apply the spring system to this pendulum problem to kind of get an idea as to what's going on. Okay, all right, so here it is. Let's separate it out a little more like so. And we're going to focus on a couple of things. So first of all, do you notice that, let's see, the mass is a positive number, right? It's the same mass that was given in the pendulum problem. And then there's no friction constant because there's no theta prime term. And then also the K value, this is where it gets more interesting. So the K value here is mg over L, the length of a lever arm, times sine of theta over theta. Okay, so this is going to be the only one that's really interesting, and the rest are just basically constant. So yeah, so we're going to focus in on the stiffness. All right, if we take a look at this stiffness, this is actually a function of theta. We could actually graph the stiffness function of theta. We could plug this in Desmos, pick some convenient values, and your graph will look something like that. All right, so you'll notice it's maximized when theta equals 0, and as we go out, it kind of comes down. All right, but here's the thing. If your value of theta, the angle at which you kind of pull this thing up, if that angle is small, have you guys seen this before? Sine theta over theta is approximately equal to 1. Yeah, if you take your calculator out and you pick a small angle, right? Like, like 1 degree or something like that. And you plug theta into sine and then you divide by it, that angle. What'll happen is you'll get a number really close to 1. In fact, these two functions are really close to each other, right? Sine theta and theta. That's why you do get 1 for values that are close to 0. So what we can do is, assuming that we're dealing with smaller amplitude motion, what we can do is we can drop this off. So we're going to take this guy and we'll assume that for smaller amplitude motion equal to 1. So now we've got kind of a simplified spring value there, a spring constant mg over L, which is a constant. Okay, so if we assume theta small, then K is a constant. It's actually mg over L, which is essentially nearly sinusoidal, because we know the frequency is given by K, and we also know the frequency is given by K over M. So if we take our K value and divide by M, the M's cancel and we'll have the square root of G over L. Okay, so what's happening here is our K value, as long as theta is small, we can approximate it using this value, mg over L. But the true variable stiffness, of course, will be off by this. It'll be off by a small amount. We'll have to multiply by sine theta over theta. So what's going to happen is, if you have small values of theta and you were to graph this, the motion of the spring using this spring constant versus this spring constant, they should be reasonably close together. Okay, so if they start with the same initial conditions, the motion of both springs, one with this spring constant and one with that spring constant, if they're held up at the same angle, should be about the same. Of course, they'll get worse over time, but they should stay the same for a while. But the problem is for larger theta values, what's going to happen is things will just get worse and worse. So what's happening here is the one that's in black is actually a sinusoidal curve, this one. But because it's a constant, right? But when you change it to a variable, it's no longer a sinusoidal curve. It's that kind of fatter curve. So this one right here, the true stiffness, the blue one, it's not quite sinusoidal. The black one is sinusoidal, but the blue one is not. And so what happens is as theta increases, what happens is the sinusoid just gets even worse. It distorts even worse. So the blue function gets worse and worse and kind of flattens off like so. And they showed you that motion in the video. This is where that pendulum is kind of getting up to here and it kind of slows down and comes back the other way like this. So that's what's happening here. And then for even larger values of theta, this is where we go beyond and we go all the way around. What'll happen is it'll just keep cycling through, and you'll get this kind of motion that will just continually escalate upward in the theta direction. Remember, theta is your angle, so you're just going to keep increasing theta if you keep going all the way around. Okay, and the last thing I wanted to show you is, in this section, we're looking at a whole bunch of equations that are mostly kind of beyond our understanding right now. We're just trying to get a bite out of a few of them just by looking at some of their qualitative aspects, but that's hard enough. But here's some other ones. So in your physics courses and engineering courses, you're going to run across some of these. So we've talked about the harmonic oscillator. We've talked about the damped oscillator. This one doesn't involve friction. We have these guys. These are the Cauchy-Euler equations. All right, we talked about those. That comes up, and they give you examples or areas of applications here. The area equation, we talked about that one. Bezel equation, modified bezel, Legendre equations. So we've worked through a few of these, and we'll probably see a few more throughout the rest of the book. Oh, here's the van der Pol Duffing, and I think that's all we did down there. Okay. All right, guys, I'm going to stop the video here. Give me just a second.